Lesson 4, gravity. In fact, universal gravity. We need to move beyond Kiowa. We need to move beyond gravity equals mg. Because it turns out as you go further out from Earth, gravity changes. So we've said that gravity is a force that exists between the Earth and masses on its surface. In fact, gravity is universal. In fact, today, about an hour ago, they made a massive announcement. They just announced that they had discovered gravitational waves. Einstein, when he came up with general relativity, which redefined, what I'm teaching you is Newton's law of gravity, which explains how to calculate it, but not how gravity works. Einstein came along and explained how gravity works. One of the predictions was that there might be, much like the ripples, if you take a blanket and you shake it, you get some ripples in the blanket. There might be ripples in the fabric of space-time left over from the Big Bang, and they've been trying to detect those for a few years, and I think just today they announced that they have. I haven't checked my email feed in a couple of hours, but this morning that was the speculation. So this is very, very timely. Gravity is universal. It exists between any two masses in the universe. Example, this diagram shows two masses, big M, let's think Earth, and little m, let's think Moon. Compare the gravity forces on the two masses. The force exerted by the Earth on the Moon is greater? The force exerted by the Moon on the Earth is greater? Or the forces are the same? You know what, once again, this gives us a chance to vote. Once again, how you hold your hand up is how sure you are of the answer. Clay says it has to be. So Clay, what are you going to pick? I'm making you vote on your own.
B.
Who says A? Who says B? Clay did.
I changed it.
Who says C? Attack or defend? Yeah. What, Clay?
Forces come in pairs.
What was that? Loud and proud. What?
Forces come in pairs.
The forces are identical. Are the masses identical? No. So will the accelerations be identical? No. But the forces are identical. The Moon and the Earth pull on each other with exactly the same force. Hey, let's even be more specific. Is the Earth pulling you down to the Earth? You are pulling the Earth up to you. Right now, when I drop this ball, yes, the Earth is exerting a force on it. The ball is exerting exactly the same force on the Earth. Why doesn't the Earth move up to meet the ball? First of all, Einstein suggests that it does, but we would say, under Newton's understanding of gravity, because the Earth has such a big mass, if F equals ma, small mass, big acceleration. Heck, I can tell you exactly what the acceleration was, 9.8 meters per second squared. Big mass, really you can try and crunch it, no acceleration. Okay. So this is the first thing I want you to realize is any two objects that are exerting forces of gravity upon each other, the force will be the same. It's one force. Doesn't matter about their masses are different. Now, going to your question, the amount of mass will change the overall force, but it's going to be the same on each one. Cavendish, and others since him, designed ingenious experiments to measure this small force of attraction between the masses. Out of the four fundamental forces, the four fundamental forces are electromagnetism, which explains magnets and electricity and light. Strong nuclear and weak nuclear forces, I always get them mixed up. One of those is the force that holds neutrons and protons together, because something has to hold the quarks together. And one of those is the force that explains why electrons, which are negative, don't just get sucked right into the nucleus because the protons are positive and don't, unlike charges, attract. So strong nuclear and weak nuclear force keep atoms in their places. And there's gravity. That's the fourth fundamental force. Gravity is so much weaker than the other three. We think it's the biggest one because the Earth dominates us so much, because the Earth has such a big mass. But I always like to tell people, if we were super intelligent bugs, if we were insects and we were super intelligent, we probably never would have discovered gravity. We wouldn't notice it. It would be such a small effect on our lives, we would be, whatever. Because we would walk up the wall and no big whoop. We would walk along the ceiling and no big whoop. Why would, no big deal. So Newton came up with the equation for gravity, but he was missing a constant. He was missing a very small number. Cavendish and others ran experiments where they found this small number, and here's what they came up with. He found that the universal law of gravitation is big G, m1, m2 over d squared. Or you'll this unit often see me write it as big G, big M, little m over r squared, because we're going to be moving in a circle, so why not call it a radius? And big M is going to be the planet, and little m is going to be the satellite, or the rocket ship, or the moon, or the astronaut, or whatever. It's a scalar equation. What's the direction? Towards the center of mass of the planet. Did I say towards the center? Yes, it'll fit into our centripetal force thing quite nicely. The real problem was finding this number here. Newton was the one who proved that gravity depends on the product of both masses divided by the square of their distance apart. But finding this number, Newton's gravitational universal constant, it's 6.67 times 10 to the negative 11, which is really small. It's 0.0000000000667. How did they find that, Clay? I'll show you later on. It was a very clever experiment because they did it with old school 1700s, 1800s. I don't know when Cavendish did the experiment, but very basic, rudimentary technology. But they managed to find a number that small, that accurate. Okay? So M1 and M2 are the two masses in the kilograms. G is capital G, not 9.8. It's 6.67 times 10 to the negative 11. Those are the units, in case you're wondering, for G. Don't bother memorizing that. And then D or R, it's the distance from the center of each mass. Put your pencil down, look up. Calculate the force between two 1 kilogram masses separated by 1 meter. Yeah, I used a bunch of ones on purpose. Well, the force of gravity between masses is big G, m1, m2 over r squared, the distance between them squared, where big G is 6.67 times 10 to the negative 11. This is on your formula sheet, by the way, on the same page that has the mass of the Earth and the radius of the Earth. There's the universal constant. What do they call it? Gravitational constant of the universe. Okay. Mass 1, 1. Put your calculator down. Mass 2, 1. R squared, 1. Kevin, what's 1 times 1? Divided by 1 squared times 6.67 times 10 to the negative 11? Oh, I weep. And this is a force, so what are the units? If you have two 1 kilogram masses 1 meter apart, that's a really small force. You won't be able to feel it. Gravity's not very big. It's just that the Earth has such a big mass that we think it dominates us, but it's weaker than weak. It's weaker than weak. Yeah, I think I should. I'm going to go back to here. Pause for a second. So you guys see how this is put together? I did that so that I can actually answer example 3. Suppose the force of gravity between two equal masses. The screen is still frozen, thank you. Suppose the force of gravity between two equal masses separated by a distance d is F. Then what will the force of gravity be if we double the distance? 4 times bigger or 4 times smaller? So you know what? Here's how I'll write that. F divided by 4. Yes? Is that okay? 1/4 is big, if you want to say it that way. What if we triple the distance? Yeah. What if we quadruple the distance? What if I double one of the masses? You know what? Let's just jot down, here was the equation. If you double one of the masses, is there a squared there? Is there a squared there? I'm only doubling one of them. That would give me an extra 2 on the top. You know what? Twice as big. What if I double both masses? 4 times as big. What if instead of moving twice as far apart, what if I cut the distance in half? 4 times stronger. What if I double both of the masses and I double the distance? I'm going to be fussy, not 0, because 0 would mean no force. I think what you mean is no change, right? Which would be, F. I'm not going to, right? The changes cancel out. By the way, where is this D right here? On the, those of you that are in calculus, if you take the limit as D approaches 0, F approaches infinity, this is what a black hole does. A black hole isn't a black hole because it's got a big mass. Many black holes have the same mass as our sun. It's that they're so small. Our sun is huge. The fact that they are so small means that as you get closer and closer to the center, the force shoots off to infinity. Or as we like to say, a black hole is where the universe divided by 0, which you really can't do, but they took a limit. Gravity, I wrote here, is usually minuscule unless one of the masses is huge, a planet or a star or a moon. Assume that the mass of the Earth is 0.98 times 10 to the 24th. That's what the mass of the Earth is. It's on your formula sheet. And its radius is 6.38 times 10 to the 6th. Find the force that the Earth exerts on a 50-kilogram person on its surface. Okay. That's going to be big G, big M, little m over r squared. I also put in brackets, note, you could ignore the size of the object compared with the radius of the Earth. Technically, I should take into account the height of the person, but compared to the mass, the size of the Earth, it's not going to make a difference. If it was 2 planets, then I'd take that into account. What's G? This is the universal constant of gravity. 6.67. You'll probably memorize this because you get sick of looking it up, but it is on your formula sheet. 6.67 times 10 to the negative 11. The mass of the Earth, also from that same section of your formula sheet, is 5.98 times 10 to the 24th. This person weighs 50. And the radius of the Earth is 6.38 times 10 to the 6th squared. I strongly encourage you to practice typing this into your calculator because we are going to be doing an incredible amount of scientific notation and squareds and exponents for the next few days, so you might want to try typing this in. Yeah, Kiowa, I'm talking to you. Try typing this in. I think I can do this in my head. Oh, sure I can. Of course I'm going to get it right. 490. Yes? I cheated.
You looked at the answer?
No. I also know, Clay, there is a shortcut for finding gravity on the surface of the Earth. The shortcut still works. I went 50 times 9.8 in my head, and I knew that had to give me the same answer as the universal one. But the nice thing is the fact that I got the same answer doing that as doing, you guys did doing this one, tells me I think this one will work anywhere in the universe. Yay. It is 400, you get like 489.99 or something like that, right? Yeah, 490. In fact, I wrote here, Clay, this should not be surprising because if we calculate using mg, you still also get 490 newtons. On the surface of the Earth, I usually don't use this to find the force of gravity. I use the shortcut mg because I know how strong gravity is on the surface of the Earth. The problem, Mitch, is as soon as I leave the surface of the Earth, it's not 9.8 anymore. Then I better use the universal one. So, in fact, until now, we've been aware of two ways to calculate G, the gravitational field. One way I think you guys all did last year, if I go to part 2, is we dropped an object. You all went to the back stairs there and you dropped it, or from the ceiling in Mr. Camosi's room, you dropped an object, you timed how long it took to hit the ground, and you used that to calculate the 9.8 acceleration. That's one way. Just using a good stopwatch and free fall. Another way would be to take the force of gravity divided by the mass on a Newton scale. You can get G by doing this. You can get G by doing this, but that leaves us with a problem. We wanted to land on the moon. How did we know what G on the moon was before we got to the moon? Because both of these experiments require me to be there to measure it. Is there a way, Dustin, that I can calculate the gravitational field ahead of time? Yes, there is. Turns out, if I know that this is gravity, and I know that this is gravity, well, if this equals gravity, and this equals the force of gravity, if this equals the force of gravity, and this equals the force of gravity, it seems to me that I can safely say that they must equal each other. True? Is there a little m on the left-hand side? Is there a little m on the right-hand side? Then holy smokes, I have just derived the universal gravitational field equation. If I want to find what G is on the moon, or on Mars, or even just 2,000 kilometers up, there it is. This equation is not on your formula sheet. Have I showed you that it's pretty easy to derive? Okay. The universal gravitational field strength. And again, we call this gravitational field strength. If you plug in 6.67 times 10 to the negative 11, mass of the Earth, radius of the Earth, you will get 9.8. So that's also how we know that this equation is correct. It gives us the value that we've measured. But if you plug in mass of the moon, radius of the moon, that's how we knew what the gravitational field strength of the moon was. If you plug in mass of Mars, radius of Mars, that's how we knew what the gravitational field strength of Mars was when we're building probes to go land on Mars. Oh, and this also gives us a means to calculate the mass of the Earth. I can try getting that by itself. So Cavendish did this experiment, and he was the first one to find a value for big G, the 6.67 times 10 to the negative 11. And one of the very first things that he did, because at that time we didn't know what the mass of the Earth was. It's not like you can put it on a scale. In fact, at that time, what they had done is they had taken shovels of dirt, measured the mass of the shovels of dirt, taken an average, because some shovels were lighter than other shovels, taken an average, and then basically said, okay, now that we know how much 1 liter of dirt weighs on average, how many liters is the Earth? Let's multiply it out, and that should be the mass. And they were wrong. So Cavendish came along. We knew the radius of the Earth. We've been able to measure that from the geometry of the sun's rays. In fact, already 2,300 years ago, the Greeks, Eratosthenes, measured the radius of the Earth quite accurately. Ah! Kohei, you going to make it? You're looking bad. Manny, he needs your help. Because that was a long blink he was doing right there. Give him an elbow or two, okay? So we've known the radius of the Earth for a while. Cavendish, as soon as he calculated this big G, said, oh, he said, let's get the M by itself, because this is going to be the mass of the Earth. How would I get the M by itself? Times the R squared over, divide the big G over. Cavendish said, okay. Now, of course, he was doing this by hand without a calculator. It took him a while, but I'd like to know how much the Earth weighs. Are our estimates correct? So he said, okay, the mass of the Earth is going to be Gr squared, well, no, GR squared, not Gr, the G isn't squared, all divided by big G. He knew the little g, the gravitational field on the Earth, was 9.8. That they had known for a while. We knew the radius of the Earth was 6.38 times 10 to the 6th squared. And he had just finished calculating that. What do you get? Clay says the answer that's on your formula sheet. Let's find out. Again, this is your chance to see on your calculator, can you just put a squared next to scientific notation? Will it square everything? You need to get good at your calculator. At your calculator. And I get the one that's on our formula sheet, 5.98 times 10 to the 24th. And this floored him because it was way too big. Way too big. And this was the first inkling that scientists had that the Earth isn't rock all the way down, that maybe it gets denser down there. What do we now believe? What's at the center of our Earth? A very dense iron core. This was the first hint that they had that it ain't rock all the way down. We still, our knowledge of what's down below us is not all that great. We've only drilled a couple of kilometers down, which isn't far at all. Everything else is hypothesis. Big earthquakes help us a lot because the earthquake waves bounce through the Earth and then bounce off stuff down there, and we can measure those. So even though big earthquakes do damage, it's also, hey, we get to see some more stuff down there. I promised you lots of time to work on the homework. I do have a couple of videos to show you as well. But for now, you can try number 1. Yep. Mr. Dewick, there's 2 masses. So take a look at number 2. It wants you to find the net gravity on this mass right here. What you want, there is no equation for 3 masses. Instead, Vikas, what you're going to do is find this force, find this force, and then add them up, because they're both in the same direction. They're both attracted. Okay? Number 3. Pass number 4. Skip number 4. 5 is cool, but I'm going to skip it. 6 is good. 7 is good. 8 is good. 9 is good. 10 is good. Ooh, here's good practice for horizontal circles. I think 11 is good. Yeah, 12 is good too, because of using principles of physics right to explain question. 2 videos.